Hello everyone, so this is going to be the 7th lesson of this trigonometric functions unit, and we're just going to start to look at applications of these trigonometric functions and how we can use them to solve some real life problems. Just a refresher, our general equations, have these four coefficients, A, D, H, and C. And for these coefficients, A is our amplitude, which we can find by taking our max and our min values, adding them together, and dividing by 2. Subtracting them. I'm thinking of our equation, our axis. Amplitude, yes, we're finding the distance between max and min, and we're taking half of that. So that's the distance from the max to the equation of the axis, or the distance from the min to our axis. D is the period. It's found using the period. D is 2 pi divided by the period. Our H is phase shift. So we need to look at first of all, are we talking about a sine function or a cosine function? For a sine function, we need to find a spot on the axis where we're increasing. For a cosine function, we need to find some point where we're at our maximum value. And how much would we have horizontally shifted to get to that point? And then our C, that is our equation of our axis. Is going to be, so the equation of our axis is always y equals c, and we can find that by taking, this time, the max plus the min and dividing by 2. We're finding the average of our maximum and minimum values. So we'll look at an example here. The average water depth in a harbor at high tide is 10 meters, and at low tide, the depth is 6 meters. The tides in the harbor complete one cycle approximately every 12 hours. High tide is at 2 a.m. So the first question asks us to sketch the graph for a 24-hour period starting at midnight. So there's a couple key pieces of information here. We're told high tide, the highest the water ever gets. So the maximum depth is 10 meters. So our max value is 10 meters. Low tide is 6 meters. So our minimum of this sinusoidal function is 6 meters. And then the tides in the harbor complete one cycle approximately every 12 hours. That means our period is going to be 12 hours. They also tell us high tide occurs at 2 a.m. So if we're sketching a graph for the first 24 hours starting at midnight, let's move this. a little bit. So the depth at 2 hours, so if we look at a function d of t, because if we read ahead in part B, they ask us to write a function d of t. So depth is our dependent variable, time is our independent variable. So the depth at 2 hours is it's high tide. So d of 2 equals 10, or 210 is going to be a point on this graph. So we can put a point at 210. We know that has to be a maximum. We also know that a period is 12 hours. So 12 hours after this, so at 2 plus 12, sorry, not 16, 14 is going to be another maximum. And halfway in between that, halfway between 2 and 14, so at 8 hours, that's going to be a minimum. And we knew a minimum was 6 meters. That was low tide. So here, this was a 12-hour time period. And then this had to be 6 hours on either side here. Always halfway in between our maximum and minimums, that's when we're hitting our axis of symmetry. So halfway in between 6 and 10, our equation of our axis should be at d equals 8. This should be 2 meters. This should be 2 meters. We're exactly in the middle. And halfway in between 8 hours and 2 hours would be 5 hours. So we're going to hit this at 5 hours. And halfway between 8 and 14, we're going to be there again. So at 11 hours, we're also 8 meters deep. And then it's going to keep repeating. So a quarter of our period is when we get to a new key point. We always have these 5 key points in every sinusoidal function. So a quarter of 12 hours is 3. After another 3 hours, we hit our new key point. Another 3 hours will be at our minimum. Another 3 hours will be back at the axis. And we won't quite make it back to high tide before 24 hours is up. So we're going to get a function that looks like this. There's our sketch for our function. Now they tell us, write the cosine function that relates the depth of the water in the harbor d with respect to time t hours. So basically we want to write some function, has to be a cosine function, d of t. So just like we did in our previous lesson, we can look at the graph and get a lot of this information. I'm going to hold this down a little bit. So we can start off with our c variable, that's our axis symmetry. Our axis symmetry is 8. 8's our max plus our min divided by 2. 16 over 2 is 8. So c equals 8. Our d value was coming from 2 pi divided by our period. So our period is 12 hours. So 2 pi over 12 simplifies to pi over 6. Our A, our amplitude, we can see from the graph our amplitude's 2. Or if we haven't found that from the graph, we can always do our max minus our min divided by 2. Then minus 6 is 4 over 2, so our amplitude would have to be 2, which again, that's what we see from the graph. And finally, a phase shift. So this is a cosine function. Cosine functions start at our maximum value. So we can use this. We could use this one if we wanted. This one's probably a little simpler. And in order to get here, we would have had to shift right 2 hours. So our phase shift has to be 2. We moved to the right 2 here. So we can combine all that into a cosine function. We have our amplitude was 2. It's a cosine function. D is pi over 6. X minus h, so x minus 2 plus 8. And because it was a function d of t, instead of x and y, we use t and d. So d equals 2 cos of pi over 6 times t minus 2 plus 8 would be an equation for this function. Final question. What is the water depth at 57 hours past midnight? Is the tide rising or falling? So 57 hours past midnight, that's way off our graph. We could keep continuing the graph, but we don't need to now that we have an equation. 57 hours past midnight, we're interested in what is d of 57? So we're going to plug in 57 for t. Pi over 6 times 57 minus 2 plus 8. And we can plug that all in the calculator. You can simplify steps if you'd like, or you can do it all at once. Just be careful with brackets. Again, make sure your calculator is in radians mode. But we're going to do 2 cos of 3.14 or pi over 6 times 57 minus 2 minus, not divide, all of that plus 8. So that is 9.9999, basically 10. Something's not quite right. Let's try that. I think I need to be more careful with brackets. So pi over 6 times 57 minus 2 plus 8. That looks a lot better. So before, I didn't have a set of brackets around the pi divided by 6, so it was multiplying the denominator by 57 minus 2, not the whole fraction. That gives us 6.3. It's approximately 6.3, and this is meters. And the follow-up part of that question was, is this tide rising or falling? So we could go through and see, okay, every 12 hours, we complete a cycle. So every 6 hours, we're changing from rising to falling. Or we can just see, oh, what happens right after 57 hours. So 57.1, if we plug that in, what does that give us? 2 cos of pi divided by 6 times 57.1 minus 2 plus 8. We get 6.32. just to refresh, let's go back to our previous one, 6.27. And we can see we're slightly above. So therefore, what was the question? The water depth after 57 hours is approximately 6.3 meters, and it's rising. So our next step is interpreting when given the graph. So this question, or this graph, it tells us a little background information. To test the resistance of a new product to changes in static pressure, the product is placed in a controlled environment. The graph represents the static pressure in this environment, measured in pascals as a function of time and hours. So we have time and hours, and we have pressure. And the first thing we're asked is to write an equation. So just like we've been doing before, we're going to come up with the coefficients for this equation. So our C value is our max 500 plus our min 100 over 2. 600 over 2 is 300. D value is 2 pi over the period. And we can see from peak to peak, that's 10 hours, or trough to trough, 5 to 15, that's also 10 hours. So our period is 10 hours. So 2 pi over 10, we can simplify to pi over 5. Our amplitude, A, how far are we from our axis of symmetry to our max and our min? So again, we can either look at the graph, or we can just do max minus min over 2, or max minus your C value. Either way, you're going to get 200 for A. And now our phase shift, we need to make a decision. Are we talking about a sine function or a cosine function? It's easiest if we talk about a cosine function because we're starting off at our maximum value as our y-intercept, which that's what happens in cosine functions. So we don't need any phase shift. So our h is going to be 0. And then we can come up with an equation. So we'll call this P of t equals our a 200 cosine of pi over 5 t, no h value, plus 300. That is one example of an equation that we could draw from this function. B is asking us to use our equation to calculate pressure at, or the static pressure at 12 hours. So what is P of 12? Well, we just plug in 12 for T. And we can break this up. We can see pi, or 3.14 divided by 5 times 12. The cosine of that times 200 plus 300, or we can calculate all at once, is 361.9. So P of 12, somewhere in here, should be about 362. Yeah, looks reasonable. That is our point here, 12,362. That should have been 0.8. 361.8, not 9. C. Find how long is the pressure below 200 pascals. So 200 pascals. There's a number of different spots where we hit 200 pascals. If this was drawn perfectly, they'd all be the exact same width. Some of these look a little wider than others. But we need to see how far is it from here to here. For pressure this time, we know is 200. We know pressure is 200, and we need to solve for T. So we'll slowly pick apart our equation. We need to subtract 300. So we get negative 100 is 200 cos pi over 5 times T. You also need to divide both sides by 200. So negative 100 divided by 200, well, that's just negative a half. Then we need to take the inverse cosine of negative 1/2. And that's going to be pi over 5 times T. And if we multiply by the reciprocal, that will cancel out the pi over 5 on the right side and just give us T. So 5 divided by 5 divided by pi, you can use the pi button, or 3.14 times cosine inverse of negative a half is, so T equals approximately 3.34 hours. Okay, so let's look back at our graph. 3.34 hours. Okay, that sounds reasonable for this one. But we need to find out what this point is now. So we know one of our T values is 3.34. What is another T value? Our maximum was at 10, so that led us to believe our minimum is at 5. So the distance from this point to the minimum should be the same as the distance from this point to the minimum. So 5 minus 3.34 will give us our second T value. So T2, we'll call it, will be about 1.66. Oh, not T2. Maybe that'll be delta T. And the second T value that we're looking for, that needs to be 5 plus this delta T. So 5 plus the 1.66, or approximately 6.66, that is our second point here. From 3.34 to our minimum value is 1.66. We need to go another 1.66 over, because this, each curve in a sine or cosine function is symmetrical. And so finally, we have these two T values, so we can subtract them. Our bigger one minus our smaller one. 6.66 minus 3.34. 6.66 minus 3.34 gives us approximately 3.32. This was all approximate. So the pressure is below a value of 200 pascals for 3.32 hours. And you would want a therefore statement to conclude that. So just quickly looking at the completed notes, it's done as an inequality. That is technically the more like technical way of showing it, like it's more accurate. This I find can be a little bit easier to kind of comprehend, and we don't have to worry about inequalities as long as we know that cosine is symmetrical. Cosine functions, sine functions, they're always symmetrical on these curves, then this works perfectly fine. Part D, at what time will the pressure be equal to 200 pascals in the third cycle? So we complete one full cycle, we complete a second cycle. When do we hit 200 pascals in the third cycle? So we were at 200 pascals. This is D. In the first cycle, we were at 200 pascals at 3.34 and 6.66. Our period is, we talked about our period was 10 hours. It takes 10 hours to complete one cycle. So our period's 10 hours. So in order to go from the first cycle to the third cycle, we need to add 2 periods. So we're going to take our T1 and add 2 times our period, 2 times 10. So 3.34 plus 20 is 23.34 hours. And our second value, we're also going to add twice our period, 2 times 10, 6.66 hours, plus 20 gives us 26.66 hours. So therefore, in the third cycle, the pressure is equal to 200 pascals at about 23.3 hours and about 26.7 hours. So look at an example of interpreting when we're given an equation now. So this example is talking about the tides at Cape Capstan, New Brunswick. Change the depth of water in the harbor and can be modeled using this equation here. So again, T is time in hours, and D is the depth of the water in meters. So first question is asking us the average water depth. And so for all sine and cosine functions, the axis of symmetry is going to be the average of that function. We spend the exact same amount of time above and below, and we have a symmetric curve happening on both sides. So our axis of symmetry would come from this 5.6. So our average water depth is going to be 5.6 meters. Now the maximum and minimum water depths, we have to do a little bit more work. We're going to take our axis and add and subtract our amplitude. So our amplitude is 4.4. So we're going to add and subtract 4.4. And that's going to give us 10 meters and 1.2 meters as our minimum. Time between tides. Time between tides, we need to look at the period. So period is 2 pi over d, and in this case our d is 4 pi over 25. So that 2 pi divided by 4 pi over 25 is going to be the same as 2 pi times 25 over 4 pi. A 2 pi, the 2 pi will cancel from there, and we just get a period of 25 over 2, or 12.5 hours. So the time between high tide and high tide would be 12.5 hours, or the time between low tide and low tide would be 12.5 hours. When does the first high tide occur? We have a cosine function. So normally in a cosine function, the maximum is going to happen right at t equals 0, but we're shifting everything to the right by 2. So our first high tide, we shifted a cosine function right by 2. So our high tide is going to be at 2 hours, or 2 hours past noon, 2 p.m. Low tide, if it takes 12.5 hours to go from high tide to high tide, low tide happens, we divide our period by 2. It's going to be 6.25. So 6.25 hours after high tide is low tide. So we need to take our 2 and add 6.25, and we get 8.25 hours, or 8.25 hours past noon is 8:15 p.m. It's a quarter of an hour is 15 minutes. We're also asked to sketch this. So we can use all this information that we've gotten. So 2 hours we're at high tide, and high tide was 10 meters. 12.5 hours after that, so 14.5, we're at high tide again. 8.25 hours, we're at low tide. So 8.25, and low tide was 1.2 meters. We're around here. And halfway between 2 and 8:15, we can be pretty approximate. It's going to be about 5, because if we actually go 5:07 and 30 seconds, that's not really going to show up on here. But halfway in between, around 5, we're at 5.6 was our axis of symmetry. So we're around here. And same thing, halfway between 8:15 or 8.25 and 14.5, somewhere around 11, getting close to 11.5, we're also on that axis symmetry. So we're going to get a curve like this. And between noon and midnight, so we've already gone above and beyond that. We only needed to go up to 12 hours. F. A particular sailboat has a draft of 2 meters. This means it can only move in water that is at least 2 meters deep. The captain of the sailboat plans to exit the harbor at 6:30 p.m. Can the captain exit the harbor safely? So we need to see what happens at 6:30. What happens at t equals 6.5? we're going to plug 6.5 into our equation. So 4.4 cos 4 pi over 25, 6.5 minus 2 plus 5.6. 4.4 cos 4 pi divided by 25 times 6.5 minus 2 plus 5.6. All of that is about 2.8 meters. And the sailboat needed water that's at least 2 meters deep, so they are okay. Therefore, the water is deep enough. Between what times of day can the captain not sail out of the harbor? So when can they not sail out of the harbor? So we're interested, when is the depth 2? So when is this equation equal to 2 meters? So we'll subtract 5.6 from both sides. Then we'll divide by 4.4. Negative 3.6 divided by 4.4. We get an ugly decimal. If we simplify the fractions, we get negative 9 over 11 is just the cosine function. So we need to take inverse cos of 4 pi over 25, inverse cos of negative 9 over 11 equals 4 pi over 25 times t minus 2. This is going to get multiplied by the inverse. And then also added by 2, and that will give us t. So we can plug all of this in. Times cos inverse of negative 9 divided by 11 plus 2. T equals 7.03 hours. So around t equals 7, that makes sense. We're at 2 hours. Now the question again was, when can he not get out? Yes, when can the captain not leave safely? So we need to see now on the other side, what is our point where we reach? Let's try this again. What point is it that we reach 2 meters on the other side? If this was drawn nicely, it would be symmetrical. And we know that our minimum point is, our low tide was at 8:15. That's 8.25 hours. So 8.25 minus 7.03 is 1.22. So there's 1.22 hours from this point to our minimum. And then we need to add that to our minimum. And that'll show us the point on the other side of the minimum. Because remember, these are symmetrical, these sinusoidal functions, these sine and cosine functions. So that's going to give us 9.47 hours. So 7.03 that's about 7 p.m. 9.47 is about 9:30 p.m. So the captain cannot sail out between 7 and 9:30 p.m. And in those first 12 hours, that was the only time we were below 2 meters. We had less than 2 meters of water. So that's the end of this lesson. I realize that I did go through this relatively quickly, so if there's anything that you want me to go through slower or go through some of these equations or some of these questions like the completed notes, let me know. You can use this method. You don't have to use the method shown in the notes. This is completely acceptable. But that's all I got for this lesson. You'll hear from me again shortly, and have a good rest of your day. Bye.